Okay, so let's have a go at doing a couple more videos on now titrations. So I just want to really give you a background about what titrations are. But first of all, set up your books nicely. Put the heading titrations, aka volumetric analysis. So they actually mean the same thing. Now, when you look up titration in just on the internet, what do you get? So you get this setup every time, and you recognize this from the style and what the different components are of a titration. It's a pretty basic technique, but it's under the umbrella of analytical chemistry. So analytical chemistry is all about working out either what is in something or how much is in something. So when you look at a packet, I'm just seeing if I've got any packets nearby. I've got a glue stick, but it doesn't have an ingredients list. So when you have a package and you've got an ingredients list, you will either have what is present, but you usually have amounts. So you'll have the amount of sodium present or something like that. The people who make the ingredients lists are analytical chemists. One of the techniques they can use is a titration. It's a really basic technique in real life. People aren't using it, but it's really important for year 11 and 12 students to use it. So it works on this basic principle. I just want to give you an overview. I'd like you to write out the subheading of equivalence point, endpoint, titration curves and indicators, because that's what we're going to go into today. So what is a titration? That's the first essential question. It is an analytical technique used to determine the concentration of an unknown solution through reacting it with a solution of known concentration. And usually that is, we call that a standard solution, as you remember from style, hopefully. And usually it's through an acid-base reaction. But it can be redox reactions as well. Basically two things that can react and we can somehow work out when they have reacted to those correct mole ratios. And I'm going to really show that here with a picture. So let's say you've got sodium hydroxide and you want to react it with hydrochloric acid. We know that the two products are water, so that's H2O liquid, and sodium chloride, aqueous. What does this actually mean? I'm going to just make that a little bit smaller. Okay, so what does this actually mean? I'll just zoom in here. We start off with a base, and we know that in universal indicator, a base comes out purpley blue. We react it with an acid, and we know that with universal indicator, that comes out red. Okay, and then it produces salty water, which salty water is neutral, and that would look green with universal indicator. So what we're doing in a titration is we're reacting two things together, and we need to find a way visually to determine when they've reacted to completion. So that is It's not acidic, it's not basic anymore, it's neutral now. And we call that a neutralization reaction. Okay. Now, what that looks like at the atomic level, and you can kind of think of it in the titration, is the following. So we have a conical flask. You have to know what a conical flask looks like in scientific diagrams. That's what it looks like. We also have a burette, and this is where the word volumetric analysis comes from, because it's really looking at volumes. That's our measurement here, volumes. We're not looking at mass, we're looking at volumes. So what you can think of is, like, let's say we start off with sodium hydroxide in the conical flask. What that will look like is we're going to have some Na plus, let's just say, for simplicity, we have 2 moles of Na plus, or 2 molecules, 2 ions, and 2 ions of hydroxide. And then in the burette, we've got HCl there. Now, what's going to happen, remember that the HCl is separated into H plus and Cl minus, and in reality hydronium. What's going to happen is the H plus will come down and it will form water. So the first one comes down, it reacts with the hydroxide and it forms water, and the chloride will just sit there. At this stage, the pH is still basic. I'd like you to write down this titration curve. This is called a titration curve. And a titration curve just measures the pH versus the volume added from burette. So it's only interested in what's in the burette, and remember that the burette's up at the top there. So the pH starts off high. Let's say that it's 0.1 molar sodium hydroxide. What that means is the pH will be, well, the POH will be negative log 0.1, so the POH will equal 1, and therefore the pH will equal 13. So it starts off at 13, let's say. Now the whole thing is your known is your sodium hydroxide. So let's say, I don't know, we start off with 100 mils. So you'll always we're getting into calculations now. So the question might be, determine the concentration of HCl required to react with 0.1 molar sodium hydroxide. Let's just say 20 mils of HCl required to react with 100 mils of sodium hydroxide. So the first thing you're doing is you're adding the HCl, okay, to try and neutralize the sodium hydroxide. And what happens is you add it and pretty much turns into water when it comes in. So it's still basic, still quite basic. And it's like you're diluting the base 1 drop of water at a time. Every time you add a drop of HCl, it turns straight into water because it reacts with the hydroxide. So the pH changes quite gradually. And this is really good for our technique, actually, because what happens is then you keep adding the HCl and eventually you'll get rid of all of the chlorides and you'll just have water there, and it turns into a neutral solution. And we know that neutral has a pH of 7. Okay. And what happens is you actually get a drop. You get a drop to 7. And then it turns green. So it actually goes from purple to green. and that's when you stop your titration. That's called the endpoint. So we're going to define those two terms in a minute. And then what happens is you keep adding the HCl. Well, you don't in real life. In real life, you stop your titration. But if you do, you get to an acidic solution, which will actually turn the indicator red. You know you've gone too far. That's called overshooting. So let's answer this question. This question is asking us to work out the concentration of HCl required to react with the sodium hydroxide. The first thing you need to think of is what's actually reacting, and it's the moles that are reacting. So how many moles of NaOH are there? Because the more particles we're going to have in there, the more HCl we're going to need to react with it. So I'm going to give you some steps to work out the, I suppose, the concentration of your unknown. So step 1, determine the moles of the known. And how are we going to determine the moles? Well, we've got concentration there and volume there. So we're going to do concentration times volume through N equals C times V. Step 2, we're going to work out the moles of the unknown. And the way we're going to use that is the mole ratio. So what we mean by mole ratio is, in the equation, how many moles of each are required to react with each other. So you've got sodium hydroxide and you've got the coefficient of 1, HCl coefficient of 1, so make sure you balance your equations. The ratio is 1 to 1. So you'll get used to this. I'm just giving you some steps for now. Use the mole ratio to determine the moles of the unknown. Okay, and step 3, determine the concentration of the unknown through C equals now N over V. So let's work that out for this question. Determine the concentration of the 20 mils HCl, so that's our unknown, required to react with 100 mils of 0.1 molar NaOH, so that's our known. So the moles of NaOH, and I'd like you to write it out like this, equals C times V equals 0.1 times 0.1. That's really important because remember volume needs to be in litres. So equals 0.01. Is it 0.1? Yes. Okay, mole. Now use the mole ratio. Mole ratio is 1 to 1. What does 1 to 1 mean? It means that the moles of HCl will equal the moles of NaOH. So the moles of HCl also equals 0.01. Now the next step is working out the concentration of the HCl through doing N over V. Okay, so concentration of HCl equals N over V equals 0.01 over volume of HCl is 0.02 being the volume, and 0.01 divided by 0.02 equals 0.5 molar. So let's just really reflect on this answer that we've obtained to see if it makes sense. The sodium hydroxide concentration was 1/5 1/5, okay, of the HCl concentration. Therefore, 5 times the volume was needed to react with the HCl. So you can always sort of use that estimation to help you out with these kinds of questions. Let's have a look at the next point. So the next point is indicator choice. Which indicators should we choose? I do want to show you this indicator list. Now, it is in your textbook. I think it's on page, got it here actually. Yeah, on page 531. So 531. And basically you've just got different indicators. Now, why would you pick different indicators? Well, it's because different acids and bases will have different pHs. So we might have a weak acid reacting with a strong base, a strong acid reacting with a strong base, etc. So we've got to pick different indicators for different purposes. But let's say you're trying to get pH 7, have a think about which indicator you would choose to get that color change at when they have reacted perfectly together. And it's really bromothymol blue would be a nice one for that. Now, what do the other ones look like? Now, this is actually a question from a VCAR exam that I'd like you to give a go now. So have a real, just think about this. Which one of the following graphs represents the pH change when a weak acid is added to a strong base? I would like you to pause it and have a think, but I'll go through the answer now because you can obviously pause it. So when a weak acid is added to a strong base, you've got to think about you're starting off basic. So your base is in the conical flask, okay? That means your acid, your weak acid, is in your burette. If you were thinking A, you would be right, because the weak acid means that it ends up with a slightly higher pH than what a strong acid would. So a strong acid is in B, going down to pH 1. Weak acid, you're going down to pH 5. Still an acid, but weak. B would be a strong acid added to a strong base. C would be a strong acid added to a weak base. And D would be a weak acid added to a weak base. Here is a nice table. I'm going to go through some examples, only 4, that I think will encompass the strong acids and weak acids and bases that you'll need to know. So an example of a strong acid, HCl. An example of a strong base, sodium hydroxide. An example of a weak acid would be NH4+. Now, oops, that's good. Another example of a weak acid is ethanoic acid. You definitely need to know about ethanoic acid. So I'd like you to get that down too. So that's CH3, COOH. In terms of a weak base, probably ammonia will be enough. Okay, so their titration curves and indicator choices will be different. So like, for example, with this particular titration curve, you want to get an indicator that's going to change color slightly higher than 7 because it's going to have to be in between the basic and acidic pHs. So what, pH 9 maybe? pH 9 phenolphthalein would be the best indicator when you're reacting a weak acid and a strong base. So you have to know how to pick those indicators. So which indicator should we choose? An indicator that changes color when the acid and base have reacted according to the mole ratios specified by the equation. Okay. And the final part of the subheading is these two definitions. And VCAS actually asked in a Year 12 exam what these two definitions were, verbatim. They just said define equivalence point and endpoint. So we're going to do that here. Endpoint is when you end the titration. So it's the point at which the indicator changes color. The equivalence point is when the mole ratios have reached equivalence. Doesn't mean that they're equal, because it could be a 2-to-1 mole ratio. So it's the point at which the reactants, could be acid base, could be redox. So the reactants have reacted, point at which the reactants have reacted to the mole ratios specified by the equation. And this is really the first part of titrations. So in summary, just making sure that I've gone through everything. So in summary, you're reacting an acid, maybe it's in the burette or the conical flask, with a base. You're then recording the volumes of each required to react. That's why it's called a volumetric analysis. And you're going to use maths and the mole ratio specified by the equation to work out the concentration of an unknown. Okay, so I will stop that there.